Welcome to the Explainer. If you're a mobile security researcher, you already know the universal pain point we're tackling. Without intercepting application traffic, you're literally testing blind. You can't test for injection, you can't check for broken access controls, and you definitely can't see the data flowing between the app and the server. And as we all know, most production apps use SSL pinning to just stop us dead in our tracks. So let's explore a playbook that might just help us completely bypass it.
Okay, let's dive into this. We've got a really great roadmap ahead for this explainer. We'll start with the SSL pinning blocker itself, then layer foundation with proxies and certificates. From there, we'll jump into dynamic hooking with Frida and Objection. Then, we'll break down specific Android bypass techniques, followed by iOS bypass techniques. And finally, we'll wrap up by bypassing those really stubborn cross-platform apps. We are going to cover every major OS and framework here.
Section 1. The SSL pinning blocker testing blind. Now, before we can actually break the lock, we really need to understand it. Why exactly is our traffic getting rejected in the first place? Well, standard TLS relies on the device's system certificate store. Normally, if you install a proxy CA, like Burp Suite, as a trusted CA on your device, the app just accepts it, right? But SSL pinning acts like a hard-coded VIP guest list. The app is literally programmed to ignore the system's trust store entirely. Instead, it checks the server's certificate against its very own internal hard-coded list. And because your Burp Suite certificate isn't on that VIP list, the app just immediately drops the connection. Boom, proxy blocked. And here we see the two main variants of this blocker. First up, certificate pinning. This checks the exact certificate, whether it's the leaf or the root, against a hard-coded hash. It is highly secure for sure, but man, it's a total nightmare for developers when that certificate naturally expires and they have to scramble to push an emergency update. Then we have public key pinning. This one's a bit more flexible. It only checks the public key portion, meaning it actually survives a certificate renewal. But listen, for us as security testers, both methods achieve the exact same frustrating result. They block our intercepting proxy CA. So our bypasses absolutely need to be adaptable enough to defeat both of them. All right, moving on to Section 2, Foundation, Proxies, and Certificates. Because look, before we start running exploits or writing any scripts, we have to build our base camp. Setting up Burp Suite is always step 1. You're going to add a listener on all interfaces, typically on port 8080. But step 3 is the one people miss all the time. You absolutely must enable Support Invisible Proxying under the Request Handling tab. You might be wondering, why does this matter? Well, it's because mobile apps often just don't send those standard HTTP proxy headers like a normal web browser would. Invisible proxying is what allows Burp to capture those direct requests seamlessly. Next up, we have to force our certificate right into the heart of the Android system. Modern apps completely ignore user CAs, right? So we have to get into that system-level trust store. To do this, you'll export your CA from Burp, convert it to PEM format using OpenSSL, and grab a specific subject hash. You rename the file using that hash, and finally, assuming you're on a rooted device, which you should be, you use ADB to push this file directly into the caccerts directory with 644 permissions. And just like that, your foundation is totally set. Section 3. Dynamic hooking, Frida, and Objection. Now that our base camp is built, let's introduce the universal keys for unlocking standard libraries across these mobile apps. Okay, the crucial point here is knowing when to use which tool, basically when it works versus when it fails. Objection is fantastic for your standard Java or Kotlin networking apps. You just need Python and a rooted device. Frida scripts, on the other hand, give you that surgical, highly targeted control. That is absolutely mandatory if the app uses native C or C++ pinning. And what if the app isn't explicitly pinning, but just strictly checking the system store? Well, a Magis module like Trust User Certs might be the only thing you need. It just automatically moves your user cert right over to the system level. Let's actually focus on Objection for a second. Running the single command Android SSL pinning disable inside Objection is just incredibly powerful. Instead of you having to hunt down the exact library the app is using, Objection just spray hooks all of these common methods simultaneously. We're talking OKHTT3, Trust Manager Implam, SSL Conscript, the whole shebang. For the vast majority of standard apps you'll test, this is hands down the absolute fastest approach to disable that pinning logic on the fly. Which brings us to Section 4. Android bypass techniques. So what actually happens when standard hooking fails? And we have to start digging into those OS-level quirks. So the crucial point is, if an app uses Android's declarative pinning rather than code-based pinning, we can actually just surgically alter the app itself. It's pretty straightforward. You use APK tool to decompile the APK, you navigate to the res/xml/networksecurityconfig.xml file, and you just look for the pin set block. Then you literally delete that block and replace it with trust anchors configured to trust user certificates. Rebuild the app, sign it, install it, and bam. It is a permanent bypass, no runtime hooking required. However, you are inevitably going to encounter the final boss of Android methods, native pinning. This is the hardest Android method you will face. High-security apps like your banking or fintech apps intentionally pull TLS validation entirely out of the Java layer and bury it directly into native C or C++ code, using libraries like OpenSSL or BoringSSL. Objection will straight up fail here. It's a massive escalation in complexity. We literally have to extract those native libraries, drop them into a reverse engineering tool like Ghidra, map out the native functions, and then write highly targeted custom Frida scripts to hook those exact memory addresses. It's tough, but it's totally doable. Section 5. iOS Bypass Techniques. Let's pivot over to the Apple ecosystem and explore the specific bypass arsenals we need for iOS apps. On a jailbroken iOS device, your absolute first stop is usually SSL kill switch 2. You transfer the dev package to the iPhone via SCP, install it using DPKG, and it injects right into Cydia substrate. That gives you a really simple toggle right in your iOS settings to just disable pinning globally. Super easy. Now, if that doesn't work, some iOS apps define their pinning rules purely in the info.plist file. In that case, you just unzip the IPA, pop open the plist, and look for Boolean flags like TSK and force pinning. You change them from true to false, re-sign the app, and you're in. But here is where things get really, really challenging. What if you've done everything right, you have all your tools ready, but the app is built on a framework like Flutter or Xamarin? These frameworks are notorious, and I mean notorious, because they completely ignore the iOS or Android system proxy settings entirely. You could have Burp set up perfectly, and the app will just route its traffic right past it like it's not even there. So how on earth do we catch it? Section 6. Bypassing cross-platform apps. Let's tackle these final bosses that just refuse to respect the standard rules. To actually capture Flutter or Xamarin traffic, we typically have to use what's called the hotspot method. Essentially, we are forcing the traffic through our proxy at the network layer itself. You share your Mac's internet connection to your phone, maybe via Bluetooth tethering or Wi-Fi. Then you create a custom packet filter rule, a pf.rules file, that forcibly forwards all TCP traffic coming from that network bridge straight into 127.0.0.1 on port 8080. You enable IP forwarding, make sure Burp is set to invisible proxying, and suddenly that rogue traffic has absolutely no choice but to flow right into your intercept window. And hey, if that network level routing fails, we can use specialized tools like reflutter to patch the compiled Flutter binaries directly. Now, what's really interesting about this slide is how React Native handles pinning. Apps using the popular React Native SSL pinning module actually have a fascinating flaw. They often store the pin certificate right inside the APK's /assets folder. You don't even need complex hooking here. Seriously. You literally just change the APK extension to .zip, open it up, navigate over to the assets folder, delete their .cer file, and paste in your own Burp Suite.der certificate. You just rename yours to exactly match the file you deleted, re-sign the APK, and the app happily pins your proxy certificate. It completely defeats its own security. No way, right? Now, even with all these techniques in your toolkit, you are inevitably going to hit some roadblocks. If the app instantly crashes the second you attach Frida, well, you're facing Frida detection. You'll need to rename your Frida server binary or patch out those static checks. What if your proxy certificate isn't in public certificate transparency logs? The app's going to reject it, which means you need specialized CT hooking. Also keep in mind, often the pinning isn't even in the main app. It's hiding inside a third-party SDK like AppDome or Akamai. And finally, what if the pinning is bypassed, but your traffic still fails? Decompile the app and check for hostname mismatches. The app might literally be hard-coded to hit a production URL that your specific test environment just isn't resolving properly. And that brings us to the ultimate takeaway from this explainer. Bypassing SSL pinning, that isn't the end goal. It is merely the prerequisite. You've manipulated the file system, you've injected dynamic hooks, you've routed traffic through virtual bridges, and you have finally successfully intercepted the clear text traffic. The base camp is built.
So the real question is, now that you can see every single request and response, what hidden API logic, injection flaws, or authorization bypasses are you going to exploit next? Thanks so much for joining me on this explainer. Keep experimenting and keep pushing those boundaries.